Okay, so today we are going to talk about properties of stochastic differential equation. So again, dxc s of x of t is equal to sum of these integrals. Again, I recall that this is an integral equation, not actually differential. And sx psi of s and x at time t at time s is just x. So s and x encodes the starting position and starting time. And we will speak about properties of this mapping. However, to simplify notation and to follow the way it's written in literature and how it's easier to read, we will switch to this notation. I will put both time variables as subscripts and x starting point as a proper argument. So this is a solution of this equation where it's that starts at s from x and lives up to time t. For our results, we need a well-known and famous result, which is called Kolmogorov, sometimes Kolmogorov-Chentsov continuity criterion. It's called criterion, so it doesn't it is not formulated as a necessary condition here. So if we have RD-valued random process with some parametric set A, which is a subset also of a good metric space, just Rm in our case, if we can find three constants, positive constants, that this holds, so D is the dimension our process lives in, then eta admits a holder continuous of any order that less than this ratio modification. Almost surely. Almost surely holder continuous. So this probability value, this as a function is continuous. So we are going to apply this to our situation where these are going to be treated as this R. So we start with the first result we are interested in, which is the existence of a good modification of a family of solution of stochastic differential equation. So there is a modification of this process. Note that here I am writing a finite t capital. It doesn't really matter because we can extend to infinity, but for estimates that we are going to write, it always assumes that time is finite, otherwise you need to include some exponential with respect to time. Because even an ordinary linear differential equation just grows as exponential with time. It can grow exponential with time. So this modification satisfies two properties. The first one, this probability one, is probability one. This mapping is locally holder continuous of any order less than 1 with respect to this metric. This is called the parabolic distance, and if you look into theory of, say, holder solutions of partial differential equations, this is a standard metric. And it's typical also for the whole theory of stochastic differential equations. The term variables always calculated with 2 times less powers than special variables. And the second condition is that original SDE holds for psi in its integral form almost surely. For proving this result, we will need to go through a number of steps. Now, to simplify notation, convention, I will consider exclusively the case D equal to 1. Sometimes we also will do M equal to 1, but it's not important right now. We will formulate results still in the general form, but we consider only this case. Nothing really changes at all, improves, etc. So we will need the following proposition. This is going to link the existence of this good modification with the Kolmogorov-Tensov continuity theorem, and essentially it will reduce it to that criterion. A good modification we are interested in exists if any p greater than 2, there's this constant that depends on p and t capital, the terminal point of time, if s1 t1 of x1 minus psi s1 t2 s2 t2 x2 taken the norm to the power p is less than c, and here we have the estimate x1 minus x2 to the power just plus the time part one plus x1 plus x2 and everything to the power p. Here s I will write it one time, and next we will always understand that x1, x2, and all our time variables are always here. Xk, they're always leaving this parametric set. Now, this is indeed a corollary of a Kolmogorov-Tensov criterion. So here stands our original process, and we just take p sufficiently large and set alpha equal to p, beta in the formulation p minus d, this beta here, d, and then beta divided p minus d over d is less than 1. So indeed, if it is now return to the main result, if we establish the existence of the modification, a good continuous with respect to all variables modification of this family generated by our SD, and we know that the same modification exists for these integrals, then it will follow automatically, this second part. Now, proving that these integrals have such modification doesn't really is not really different from proving the same for the psi s of x of t. So I will just assume that we know that for stochastic integrals I will prove only the first part. Then the second will follow automatically because everything is continuous. Almost surely you just take the intersection of those set of all those sets of full probability and you conclude the proof. By the previous proposition, then it is sufficient to prove that star, I will denote this estimate by star, holds. Now, let's do it in a number of steps. So step 1 is going to be devoted to the case S1 less than S2 less than T1 less than T2. So S1, T1, S2, T2. So this is the situation we have. And set delta S, S1 minus S2, delta T, T1 minus T2, and delta X, X1 minus X2. Now, theoretically, you need to, when doing the reasoning we are going to do, you need to consider separately this integral and these integrals. But overall, we will only consider just stochastic integral because it's typically harder to work with. And also, if we use another notational thing that we already used when we were discussing the Ito-Taylor expansion, and we can just set W0 equal to T and sigma 0 equal to A, then psi S1 T1 X1 minus psi S2 T2 X2 is less than when you take it to the power P, the following expression. So here going to be the sum from 0 to m. So we include the Lebesgue integral in the sum, even though it should be treated a bit differently. Sigma k r psi s2, this is part, s2r dwk r p plus other and x1 minus x2 p, this part, and now the middle part, plus sum over k 0 to m s2 t1 sigma k. We'll actually write the special argument first. In order for psi s2r x2 r dwkr again to the power p, closing the bracket. So I will denote this decomposition of the estimate as the sum of three terms, and we can work with them separately. For that, we can prove an interesting result. I will call this lemma. And we will actually use this lemma, the second part of it, later. So it goes as follows. For any q just in R, not positive, not greater than 0 or greater than 2, we have the following two properties. Exist C that depends only on Q and T capital, that mathematical expectation 1 st to the power x squared. We are in one-dimensional case. Call to the power q, which can be negative. It still satisfies this inequality. And second part, again, there exists C that depends on Q and T, probably different, such that for any epsilon greater than 0, so it doesn't depend on this epsilon, mathematical expectation x1, x2 squared to the power q. This is positive, so I'm not worried about q being negative, is less than delta x squared to the power q. We will not need q just real in the first part, but it's an interesting departure from our usual routine. So let's prove it in this way, because it also introduces somewhat new technique, I would say, or maybe not a technique, but a trick. We will use the Ito formula here, and not just LP estimate, because LP estimate doesn't work for negative, or even powers less than 2. So this is a good example. Let's do with epsilon even, because here you can put epsilon to, maybe you don't really need it, q. So the first derivative is going to be 2q1 plus x squared q minus 1x. And the second derivative is going to be 2q1 plus x squared q minus 2. Here 1 plus x squared, if we differentiate this factor, plus 2q minus 1 x squared, if we differentiate this part. Yeah. Set eta of t equal psi s tx. And if needed, you can use the equalization technique, but in the end, we should arrive at something like that by using the eta formula. 2q mathematical expectation from s to t. The first derivative, the r squared q minus 1 eta r dr plus the correction. With respect to stochastic part, the second derivative, eta r squared q minus 2 times this bracket, which gives us 1 plus some constant, r squared, sigma squared kr dr, where a tilde of r is just a. This, and sigma k of r is just sigma eta r k. Now here, in this part, for instance, axr is less than by the standard assumption A2, which gives us a control of this growth. And this sum also by A2. Now, if you substitute this here and replace this with these estimates, you will get that mathematical expectation f eta of t is actually less than some constant 1 plus integral from s to t mathematical expectation r dr. So you can easily conclude by the Gronall-Bellman leap. So this is illustrations that you need to treat deterministic part and stochastic part slightly differently, but again, it's the whole theory constructed the whole way, so it doesn't make a really difference. For the second part, you actually pretty much do the same, but instead of this correction, because it's a difference now, and your process, so step 2, the second part, your process is going now to be this difference. So this is going to be a psi s r x1 r minus s r x2 r, and sigma kr is going to be sigma 1 r minus sigma k psi s r x2 r. Now using A1 Lipschitz continuity, we can finish the proof. If you want to do this as an exercise, pretty much the same calculations. Now, we can now proceed to estimating our terms. So I1 was this part. What happens from T1 to T2? Let me write it in this form. T1, T2 sigma k psi S2R X2R DWR. Now P is greater than 2, so we have the estimate for the P's power of a stochastic integral, or you just can use a Burkholder-Davis-Gende inequality if you want more involved machinery, but this is going to be estimated in this form. 2 minus 1, mathematical expectation T1, T2, sigma k psi S2R R of x2 squared dr 2p. Yeah. You can use here either the Holder inequality. Here, let's us recall. Holder inequality gives the following: a positive AB f of s ds p over 2 is less than 1. We write this is the product of these two functions, p over 2 L u AB, such that 1 over q when r over 2. This is just 1. So q is equal 2 minus 1 equals that p over 2q should be equal p2 minus 1. And this is exactly 1 to the power p over to this power lq ab is just b minus 1 to the power p to q by the definition of LQ norm, just b minus 1, 2 minus 1, this part. I want to recall these two calculations because I keep mixing them during the course. You can use either the Holder inequality to arrive at this, and the Burkholder-Davis-Gandhi, or you can use the Jensen inequality, is it if we have non-negative random variable that is less than 2, which means that if you do such type of integrals, now this is a probabilistic measure, by we obtain this by dividing. This is less than 1 AB FP2 SDS. So again, this is why we have 1 less power. But this now can be estimated in term of psi by A2 and so on. And we have the estimate for the solution of the stochastic differential equation from previous lectures. I'm not going to write all the details because too lengthy, just too lengthy. For A2, let us see what A2 we had. A2 was, where it is? A2 was the difference between, yeah. Is less than, again, just delta xp plus psi s1 s2 x1 minus starting point to the power p. And again, we have already estimate for this from the previous lectures. So we are left with the third term, and Here one can apply lemma 2 for Q equal to P, or P over 2, I think. I'm not going into details because you need to be careful to obtain precisely this form of estimate. But you can combine everything in a careful manner to obtain it. So we indeed have existence of good modification. The next result is central for this lecture, and the main part of it, essentially. Let the coefficients of our equation belong to the space C1 alpha, which means that have fast derivative in multidimensional case directional derivatives with respect to the standard basis. And those derivatives are locally, no, not locally, globally, Holder continuous, and additionally with bounded derivatives. Then, with probability 1, I am writing probability at the beginning, so everything that happens after happens on the same set of full probability. For any k living in the set of indexes up to our dimension, and st, the mapping x is in C1 beta for any beta less than alpha locally. And these derivatives are unique, strong solutions of the following system of d squared as d's, one-dimensional as d's. Let's write them. So here I will use the following notation. So d psi st x, else coordinate can be written using the notation we introduced a moment later, from 0 to m, a moment before, li psi stx, the whole process, all coordinates, t dwe of t. So instead of sigma k that we used to write, we wrote everything in coordinate form. And then the stochastic differential equation, that the derivative with respect to the case variable after taking the else coordinate is this double sum, g from 1 to e from 1 to d, mixed a bit. It's better to write g here. It makes more sense. Sigma lj psi stx t times the derivative with respect to L, with respect to K, wait, with respect to E. No, with respect to K, with respect to K, with respect to K of psi. One moment. For psi stx E, dwg of t. going to know this to start. So here, this notation should be understood as follows. dxi lg psi st of xt means that we take derivatives with respect to, say, y of this function and then put y equal psi st of x. So remark, so how it is obtained? By just formal differentiating the coefficients. So if we just formally take the case derivative of this stochastic integral, informally, I of R, J in our notation. This is going to be we take the full derivative, we differentiate with respect to all the variables, and then we differentiate with respect to xk, what is obtained by doing this differentiation. So we need to differentiate with respect to dxk exactly as the ice coordinate, dwj var. So this is how you remember this formula. You just differentiate it. So for instance, for example, if we have just one-dimensional situation, we have the derivative should be with respect to first variable t derivative st of x dt plus sigma prime with respect to first derivative, first argument d double. Now, before continuing, we need to say about this SD, because this SD is different from what we considered. It's different in the way it's coefficients that we considered before were functions of two, x and t, two variables. But now these coefficients are random in the sense that we have an extension of the theory of strong solutions to include the following. Omega dt. Again, I am considering just one-dimensional case. D double. Assuming our standard assumption on the coefficients hold uniformly in omega is probability one. So they hold uniformly in respect with t. Uniformly in t, they also should hold uniformly in omega. And obviously we need some kind of measurability. So we need these two mappings, xt to omega, which sends to xt omega, are progressively measurable. Progressively measurable. Again, it's slightly an overkill, and adapted would work too. Now, if you look at the situation, and you will think about the existence and the uniqueness theorems and their proofs, you will see that you can actually repeat all the proofs to cover the situation, because this holds uniformly and this guarantees that all measurability issues can be solved. Obviously, we're not going to do this. Nobody ever does. But you literally can go, and I actually recommend you do this at least once in your life, to go through the proofs and check that this works. Localization techniques would work too, etc., etc. The solutions we obtain are going to be continuous with respect to time variable by the very same arguments we used to prove that result for our initial SDEs. So we can believe that this is a well-defined system. Now, to understand what happens in our case, we have the following coefficients: sigma Lj psi st of xt dxk psi st x y, and it can be written as tx omega, where x and this function is just x the is coordinate here of our process. This is our dimensional process, because this is the derivative with respect to k, but taken of this is derivative with respect to k applied to every coordinate of this r devalued random process. So this times this expression psi t of xt, and this is some function g of omega and t, because it doesn't depend directly on the function that is supposed to be a solution. This is the solution. We are solving this equation with respect to this process. It doesn't appear here directly. So this covers our situation, and we can conclude that this system is indeed has a strong unique solution. So we need to show two things. We need to show this derivative exists, that they are good in this sense. And the second thing, we need to show that these derivatives indeed satisfy this equation. Then we can use this analog of this theory of strong solution to conclude that they are strong and unique solutions. So this is the second stage of our plan today. We will need to define an additional process, which is 1 over y psi st x plus y minus psi st. Back to one-dimensional case. T of x. Here s lives here. X lives in R, and y cannot be, for obvious reason, equal to 0. Now, remark. So if you want to discuss the multidimensional setting, then you would consider still y in on the real line excluding 1.0, but here you would put something like y where ek is the case element of the standard basis in RD. But again, nothing really changes it much when you work in one-dimensional case. It does get computationally much heavier, I would say. So you need to be more careful, etc. But the idea is the same. For that, I will need proposition. For any p greater than 2, there exists a constant to the power of p is less than this constant, And here we have something similar to what we had for just a solution, but now this alpha appears here everywhere. Note that this is the reason why we are talking about local holder continuity, essentially. It's also a reason. I am actually not right. The Kolmogorov-Cherntsov criterion is inherently local. I'm sorry. This is not the reason. The reason is because it doesn't produce global holder continuity in general. If you recall the proof. So step. The first step we need is quite obvious. We need to be sure that we can even discuss such things. That this is uniformly bounded. And this introduces a trick that goes through the whole theory and will help us a lot. That for one-dimensional, it also works for multi-dimensional setting. For any continuously differentiable function, the following holds. So to understand why this is true, just write it as follows. And integrate. This is going to give you this. So now using this formula for fixed R, we can write the following. Plus u sin x plus y minus psi sr of x, comma r psi sr x plus y. Because this is the difference, this is just the difference of two solutions. This minus this. So we consider only the case we do not have drift and m is equal 1. So it's only the stochastic integral. Because as I said, dealing with Lebesgue integral is typically easier. So let us introduce a notation, say of this form. I want to include everything inside to it. Psi s rx plus u. I'll write here delta psi rx y. Where this delta is going to be delta psi s rx. Here's the difference psi s r x plus y psi s r x. And then we can rewrite eta st xy. Now dividing this by y as 1 Oh, by the way, I forget to put here initial condition. The initial condition dxk psi stx L when s t equal to s is obviously just the indicator that k equals L. Just very, if you know the corresponding result for the Malawian calculus, very similar, but the initial condition is different. Plus integral from s to t dwr. We have just one Wiener process, so I drop any subscripts. P s t x y eta r x y. Now, because everything, all derivatives are bounded globally, this is bounded. So if you take the derivative, again, using localization, if you want, we obtain 1 plus st. This constant depends on the supreme derivative of sigma. So the Gronall-Bellman gives you the result. Now, step 2. I will consider only the case T1 equal T2 equal T. S1 less than S2. Then this difference that we need to estimate to prove our main result can be written as the sum again of terms. So we have something that happens before S2 starts, and here we just have S1 R X1 Y1 eta S1 R X1 Y1 DWR plus S1 S2 2T here DWR. Now purists would blame me and criticize me heavily for writing this differential here and then here, but I think it's much easier to understand when the differential written just after the sign of integral it belongs to. I was never able to understand why people are writing iterated integral in the way that the derivative, the differential go like this. By the way, I never was able why you would do this. But a lot of people will do this and like this notation. And here we have the difference, so I will need to be careful. The S1, R1, X1, Y1, 1, C R1, X1 plus U delta psi S1 R1 X1 Y1 R minus eta sigma 1, but for S1, S2, R, X2, Y2. So the same expression, but the subscript changes from 1 to 2. This is the difference. And again, this is I1 plus I2. Now, I1 is not a problem because this is bounded. This is also bounded in LP. So when we do LP estimate of this should be estimated in terms of S2 minus S1 to the power P. So we just immediately can conclude this should be something like this S1, S2, mathematical expectation S1, eta of S1 R X1 y2 to the power pdr. This is just bounded by the previous step. So this whole integral is estimated by some constant times s2 minus s1, which gives rid of this minus 1. So it immediately gives us the answer. Here for I2, we need a bit some work, which is step 3, I2. So let us introduce zeta k, r of u. This is this expression. And delta of r is just this difference. It's easier to write. And I will write I2 as the integral from s to t f of r dwr. F is now written here. This is f. All this is f. And I will work with it directly. So this is less. I want to add and substitute in this expression to make use of the triangle inequality. So I want to make this part and du zeta 1 r u r minus zeta 2 r u r. So I am adding and subtracting sigma 1 first, the derivative of sigma with respect to the first variable of zeta 2 times this. No, I imagine subtracting the opposite. S2r, then it should be. Let me think a moment. Du, and I want. No, it's not correct. It's not correct. It's not correct. It's not correct. Yeah, I am adding and subtracting eta s2 r x2 y2 zeta 1 r u. This, I am adding subtracting this, then it should work. And it the difference absolutely. Plus, this is I obtained by subtractions, and so this is going to give me this part, modulus, integral from 0 to u du, and here we have the difference. Now we have the difference. R minus sigma zeta 2 ru. And here, no, this is bounded, just bounded. So it's just some constant delta of r. This integral is just 1. Here we get, this doesn't go anywhere, but here we obtain, again, integral remains. To the power of. This is by Holder continuity. Now, this expression, G, can then be estimated directly and immediately as this Rx 1 minus xi s2r x2 to the power alpha plus u alpha xi s 1r x1 plus maybe with some constant. This is because for alpha less than 1, this is just alpha b. And this difference is the difference of these two expressions. So this is calculated. Maybe here should be 1 plus alpha, something like that. It doesn't matter. It does these and integrate with respect to u and get rid of these terms. They don't influence anything. So let's try to recollect everything and put some root estimate. I'm saying root because we don't really care that much about being very precise. So you can track everything to obtain a proper form of the estimate. Now, this is going to give you t minus s2 to the power. By doing the same Holder or Jensen inequality, we will eventually should arrive at ETR. This is for this part. Again, this is bounded by step 1. So this is just to the power, to this power, which is exactly, more or less exactly what we want. And here we get the second term. dr. And here stands mathematical expectation s2r x2 to the power p times what you obtain from this part. This term and this term. We integrate over u to get rid of this expressions, and we still left with this. So here stands psi s1r x1 minus psi s2r x2 to the power alpha plus the same for these two. To the power alpha and to the power p. Let us consider the second integral. We already have dealt with the first one, integral. So let us use the Cauchy inequality inside of this integral. dr so it's going to be 2p 1/2 times mathematical expectation psi 1 r x1 minus psi s2 r x2 to the power 2 alpha p 1/2 plus a similar term for this part. Similar. Now, this is just bounded by first step 1. We established it for any p. This is bounded. For 2p, it also works. And here, we can use the lemma we proved. Let me find it. Here. Here we need the second step of this lemma. Not for Q real, just for Q greater than. Theoretically, we can use this for Q only greater than 2 by taking P in the original statement large enough, but actually we use it in this direct form. It includes some epsilon, but you can go to the limit with respect to epsilon. It's the left and right hand side. It's very easy. And now collecting everything together, we can conclude. I am not going to do this. Now step 4 is what happens if we have, say, this inequality. That's one. But it's actually easy. We take everything at this moment of time and W known expressions. Now, this is covered by step 3, and this can be dealt with in a very similar manner. I will leave this an exercise. This finishes the proof of this estimate. The next step is the process eta st xy when s and t live here, y lives here, can be extended to the set y equals 0 in such a way that the extension, I denote eta tilde, is locally Holder continuous of any order less than alpha. Corollary would be as follows: with probability one derivatives dx1 psi st dxd psi st exist control exist. Why? Because they coincide st x0. This is exactly these limits. So if you can do this on the set of the full probability in this proposition, the first one, then it immediately yields this corollary and the existence of derivatives. Because at s txy is exactly 1 over y is a difference. So this limit here is exactly the value of this derivative if it exists. Now we need to prove this proposition. So note that if we fix s tx, then for any sequence of numbers converging to 0, this sequence I will denote it kappa y1 because everything else is fixed. This sequence maybe it's more gradually satisfies that to the power p is less than c. This constant depends on s, t, and x. And here stands this part, alpha p. Now, by taking p large enough, oh, we don't even need that. This immediately gives it the sequence is Cauchy in, say, L2 omega. By the definition, the distance between all the elements uniformly converges to zero because of this. This means that it has a limit in L2. Now, for any other sequence that satisfies the same relation, that is convergent to zero, these two limits are going to coincide almost surely because they are L2 limits. Now, we can take any sequence, say dyadic numbers or whatever you want, and that means that we obtain at least some limit for this fixed st on x of these expressions. Now, take any, say, fixed. This gives some values like our two limits. Now we can consider the extended process, which just equals y doesn't equal zero, or this limit and the limit exists. This and say zero otherwise, or p, or pi, or 2 pi. This is our new process. And now we can use the Kolmogorov-Chentsov criterion to check that this process, this new process, is Holder continuous, including now y equal to zero. This is true because this estimate holds for before y1 and y2 hit zero, but it's all by continuity of these expressions, is going to hold also for y1 equal to zero or y2 equal to zero, or them being equal to zero simultaneously. So it's about Kolmogorov-Chentsov criteria because it doesn't impose many assumption on the joint measurability of the process you consider. The stochastic process is a collection of variable parameterized by some parameter. And actually some versions of the Kolmogorov continuity theorem are directly, explicitly stated the terms of continuous extensions from some dense subsets, etc. Especially this is important when you deal with general martingales because they have jumps. So we need to be more careful. So by the Kolmogorov-Chentsov, whatever you prefer, Kolmogorov continuity. There we conclude. Now we are left with one task of proving that we indeed have the representation we want. So derivatives, spatial derivatives psi st are given by solutions of, I think I put 2 stars there. So the idea of this part of the proof is pretty clear. You need to pass to the limit. It's just to check that everything works. Again, we consider only the case when m and d are just ones, and I don't really want to care about non-stochastics, the Lebesgue part. So this derivative then is just limit, almost surely, just to zero. It should be for both direction, not from only positive. And we already know that this is the following expression. It can be written eta as rxy integral from 0 to 1 du sigma prime with respect to the first variable psi s of rx plus u psi s of rx plus y minus x r. We established that in the previous proof. Let me denote this whole part by f r x y. Then let me introduce new function, which is going to be equal minus just the derivative xr at point x times the expression that we want to obtain in the limit psi s r x r. Now, it's easy to see because everything is continuous that this goes to 0 almost surely when s t x r s r x. Now, by using the effectively the Ito duality, it's then sufficient to prove that this integral g over xy squared dr goes to 0 when n goes to infinity. Then it will give us the convergence of the stochastic integrals, and can just go to the limit in the left and the right hand side. This will converge to psi prime. This will converge to exactly the representation we are interested in. Now, to prove that this holds, one can use the standard trick of iterated applications of applying the Lebesgue-dominated convergence theorem twice in a row. So firstly, for any fixed R belonging to this domain, to this interval, closed interval, goes to 0. Why? Because this goes to 0, as we just said, almost surely, and this expression has a higher order, because this expression is the sum of something well-bounded. This is bounded, this is bounded, this is, and this is locally at least bounded by what we proved on step 1 on the previous proof. This is the limit of well-bounded expression, so they have higher moments. Zero almost surely, and grxy squared have as a family with respect to y have higher moments, and if they have higher moments, they are uniformly integrable. Since they are uniformly integrable convergent almost surely, they are convergent in mean. And second, gr. Now, we already know by step 1 that this is converging to 0. But again, it has higher moments. So using exactly the same, you can establish this convergence. Or you can just combine these two arguments and consider the dominated convergence theorem with respect to this product measure. Actually recommend writing everything. Fill in all the details. But it's more of a problem from probabilities than anything really interesting. Now, obviously, one can then iterate the whole procedure of reasoning to obtain the theorem that deals with higher derivatives. Assume that A and sigma are k time differentiable with locally Holder continuous of order alpha and bounded derivatives. Then the process psi st of x again has a modification such that with probability 1 psi st locally for any beta less than alpha, so locally Holder continuous of any order less than alpha, and the corresponding SDs can be obtained by formal differentiation of the original SDs, by formal differentiation of coefficients in the original SD. And the SD for derivatives is obtained by formal differentiation the original SD. Now, so for instance, example, again, one-dimensional case, the second derivative satisfies the stochastic differential equation with coefficients of the following form. We need to differentiate this expression, which immediately gives us second derivative plus, now we differentiate this twice with respect to the first argument, squared. Again, one can see that you can repeat the proofs, all estimates of higher orders would exist, and so on. Now we have enough time to actually put in a small chunk of discussion of the family of transformations of the real line that is generated by this process associated with the stochastic differential equation. The family psi as t is effectively a family, as I say, of mappings RD to RD. And is called a stochastic flow associated with the original D. In particular, we established that this composition works with probability 1, which is actually a very strong result. So this is indeed like a semigroup of transformations. This has some algebraic properties to it. And under quite large and more or less expected set of assumptions, such as Lipschitz continuity of coefficients, such transformations are actually homeomorphic. Homomorphism is a continuous mapping such that its inverse exists and is also continuous. Now, proving this is actually quite long. It requires some topological arguments, at least in known proofs. So we cannot really fit it in this course, but we can still prove one particular result that is of interest, mostly because of the method of the proof. And it also just nice because it makes use of something that we already proved, more precisely lemma 1. So let us recall lemma 1. I think this is the second part of the statement. For any q, there exists C that depends on P in Q T capital, that this difference we will need the following proposition. Let us introduce zeta stxy is 1 over psi st x1 minus psi st x2. And then for any p greater than 2, exists a constant that again depends on t capital and p, such that for any epsilon greater than 0, there is a good estimate for this random field. S1 T1 x1 y1 minus zeta S2 T2 x2 y2 to the power p is less than c epsilon minus 2p. We cannot get like really good estimate for obvious reasons. And here stands essentially the same parabolic distance to the taken to the power p. With this correction that the temporal part should also be multiplied by the linear growth condition. Now, and this happens for all time variables, but under additional condition that minimum of this expression should be slightly away from 0, because it's not defined when x1 equals y1, for instance. Now, the proof is actually not hard. Let us consider, let us denote this Z1, and this is Z2. And let us consider Z1 minus Z2 to the power P. And this is 1 over something like this. Let us introduce notation kappa 1 is psi S1 T1 X1 minus psi S2 T2 X2, and kappa 2 is going to be psi S2 S1 T1 Y1 minus psi S2 T2 Y2. And then this should be less than detail Z1 to the power 2, Z2 to the power 2. And here we will just take the common denominator, and this will end with kappa 1 to the power P plus kappa 2 to the power P and some constant before. Now we can use twice the Cauchy inequality. We already used it once in our previous, but we firstly use it by doing this decomposition of this integrand. So this is, and then we use the Cauchy inequality second time here. So this will produce Z1 to the power 4p 1/4, Z2 to the power 4p 1/4 times mathematical expectation to the power 2p 1/2 plus mathematical expectation kappa 2 to the power 2p 1/2. Then now this is the difference. We already have the estimate in what we discussed previously. And for this part, one can use this lemma because Q now is negative. This is 4p, and so we need to take. So, for instance, here we have 4p to the power 1/4 is less than maybe I mixed up x. No, I think I did not. X2 to the power minus 4p. And this is delta. Why? Because this is for p, but Z1 is already theta, which is 1 over. So here Q should be taken minus 4p. This gives us this. Now, combining everything together, we can conclude. And now we can formulate the proposition. The map psi st is bijective, that is 1-to-1 for all st almost surely. Note that one can say, maybe we can use this estimate to prove the same without going through all these details, but essentially you cannot because we want this to happen for all st simultaneously. And the way to do this is effectively you take p in the previous proposition large enough, and you use the Kolmogorov continuity theorem, then this process, the process zeta stxy, when is continuous, has a continuous modification. Almost surely. Almost surely. And this implies that it's well defined. And this is well defined, this means that it can never be infinite. That effectively is the whole proof. Now, to make it work for the inverse and to establish that it's indeed the homomorphism, as I said, you need a bit more involved argument, so we will skip that. This is essentially all for today. Does anyone have questions? Good. Then see you next time on the very last lecture of our course.
Thank you. See you.
See you.